Good morning and good afternoon to everybody. Welcome to this workshop at FrED and FrED Factory Summit 2026 here at Tec de Monterrey, Campus Ciudad de México, Campus Mexico City. And today we're going to take this modeling and controlling FrED spooling motor. My name is Patricio Gómez Carrillo. Here are my colleagues Jimena Fromo Garcia and Diego Emiliano Guzmán Méndez. Today we are going to talk about something that is embedded in the heart of modern engineering, the control of dynamic systems. And we won't do it abstractly, we'll do it with a real device in our hands, FrED, the fiber extrusion device. Over the next few hours we're going to talk about some theory and we work it all the way to and to a real and working control implementation. So bear with me. Workshop, before we dive in, I want us all to be clear on where we are headed. This workshop has four concrete objectives. Build an intuitive understanding of control systems. You will leave here with an intuitive understanding of what control is, why it matters, and how performance concepts relate to real systems. They are not just equations on a whiteboard. Second, we will show you how to model uh, and modeling control concepts that directly apply to the real physical device that we have today, FrED. Third, we will guide you through how to obtain usable model when we don't know the parameters of this physical model. We will do it by using MATLAB tools. And fourth, you will be able to compute PID gains and accurately compute them and implement them in simulation with Simulink and in hardware, in this case FrED, and compare the evaluation and evaluate the comparison between the two responses, the physical one and the experimental one, the simulated one, as you may see. On today's agenda, we have organized it in six major topics. We first will understand FrED as a control and educational platform, define some concepts, some modeling concepts, some um, uh, control concepts. Then we will talk in dynamic modeling of the spooling motor, PID design, and system identification using least squares. And finally, experimental validation with the FrED device. It's a complete journey from theory to practice, so let's get started. We have a lot of fun stuff to do today, so let's get right through it. So first, let's begin with the introduction section. We're going to revisit some of the topics that we've talked in the last few hours in the workshop given by my colleague Adriana. So yeah, um, first we need to ask this question: why is that we use FrED for learning control? Why is it useful for control? So FrED, as you may have noticed from this whole summit, is a really special and really creative way of solving a problem, which we will get. I want you to get to with me, and this is a fiber extrusion device, also known as FrED. FrED is a modular scale manufacturing platform designed to mimic key parts of the optical fiber production. It combines mechanical actuation, thermal processing, sensing, and digital control. This setup lets us, as students or as researchers, study manufacturing process from a control engineering perspective and build experiments around FrED. We can experiment with the real physical tool instead of just simulating or modeling or just seeing what will happen in a safe environment without the risk of getting to mess up a large machine that costs a lot of money. It not only limits to fiber extrusion, I mean every other machine that implements control in manufacturing. So let's begin with FrED subsystems. We're going to talk about what composes FrED. First, we have um, uh, the part of each subsystem has a specific task. The most important thing is that they don't work independently. Instead, they form a coupled system where changing one part directly affects the other. Starting from the top, we have the extrusion subsystem, which is responsible for heating the polymer, in this case the glue, and feeding the material into the system. Right after that comes the cooling system, which regulates how quickly the material solidifies. And the cooling rate is really important because it influences the physical properties of the fiber. And next we have the measuring device, which is a high resolution, high presumed camera that feeds the images into a computer. This computer is charged with a computer vision algorithm to estimate the fiber diameter in real time. Then we have the spooler subsystem, which uses a DC motor with a gearbox to pull and wind the fiber. By changing the spooling speed, we change the tension applied to the fiber and directly affects the final diameter, which is, we'll get to that, but this is the reason why we will be implementing a control together in this motor, specifically this subsystem. Finally, everything is coordinated by the control subsystem, which is a microcomputer, Raspberry Pi. It has power electronics, which reads the measurements and runs the control algorithms. Because all of these subsystems interact dynamically, FrED is behaving very much like a real industrial manufacturing process, where multiple physical processors are embedded together, coupled together, and must be controlled to ensure simultaneously to ensure a final uh, product quality. All right, now let's formally define what we are talking about. Control is a discipline that studies mathematical tools, theories, and algorithms that enable dynamical systems to operate autonomously or with minimal human intervention. This is one of the most used definitions, and in my opinion, one of the most complete definitions of control, because in real engineering systems, especially in manufacturing, the objectives of control go well beyond just simply reaching a desired value. It's about balancing requirements that compete with each other. The speed of response, we look for robustness against disturbances. We also want to optimize energy consumption, make our actuators last as long as we can possibly can. Um, that's why we control the actuator degradation by taking care of it, and we also ensure product quality. That's why control is just not about it's not just about reaching a value. It's about making the system perform optimally on the real world constraints. And why are we going to model what are we going to model and why? First, the fiber diameter regulation is governed by the mass conservation principle. Assuming state conditions, which mean melt viscosity, mass flow rate, and die swell remain constant over time, and also assuming that our material is incompressive, we can say that volume flow rate entering the extrusion subsystem must be the equal to that exiting it. Here we have this formula: A1 V1 equals A2 V2, which pretty much represents volume flow rate, what I've just said, and we can agree that we end up with this relationship, which states that d2 is equal to d1 times the square root of v1 divided by v2. This expression proves the necessity to control the spooling speed, since the output diameter it's inversely proportional to the square root of the spooling velocity. This means that small variations in this motor speed results in amplified changes to the diameter. That's why a controller must ensure That's why our controller must ensure a fixed spooling speed. And in the concrete case of FrED, control guarantees a stable spooling speed, which, as we've stated before, ensures a constant fiber diameter. That's why we will control this motor today. By regulating variables such as speed, motor, and heat power, the control system keeps the process stable despite disturbances or variations in maybe material conditions. This obviously ensures that the fiber is produced with a consistent diameter and quality, which is critical for operation purposes, for the fiber to transmit data accurately, and this makes the manufacturing process uh, robust.
Now let's start with the history of control systems. So the first automatic control system was first developed over 2000 years ago. The first control device on record is thought to be the ancient water clock of Clepsydra in Alexandria, Egypt, around the 3rd century before Christ. How did this system work? Well, it allowed water to flow out of a container through a hole at a roughly constant rate, and the level of water indicated how much time had passed. However, this system was considered to be an open loop system because it had no feedback mechanism. This means if the flow rate changed because of the pressure or temperature, the system would not adjust or correct itself. Now let's see a video. What did you observe in the video? What is that? So this is the first closed loop system. It was built during the Industrial Revolution in the 18th century. And during this time, steam engines were the primary power source in factories, but they had a huge practical problem. Every time the load varied, the engine's rotational speed changed as well. Those fluctuations could reduce efficiency, damage the machinery, or even cause dangerous failures. So, in order to solve this, the Watt's centrifugal governor was invented, and this machine could actually react to the changes in the engine's rotational speed, that changes that human operators were too slow to handle. But how did it work? As we observed from the video, there's a motor, and the motor rotates. Then there's an axis that rotates as well. And in this axis, there are two spheres. When the motor's speed increases, the sphere's distance or separation will start to increase. Will start separating. The spheres will start separating. And this separation actually creates the bulb to move. The movement in the bulb based on the measured speed allowed the governor to maintain an stable operation without the need of human intervention because it allowed to release vapor, to release steam. And this machine actually introduced a core idea that is used in modern control, which is feedback. And feedback is a way of correcting the input by comparing the desired output with the actual output. Let's look at a more familiar example. What about the pressure valve on a pressure cooker? So the pressure cooker keeps the pressure near a set point using a spring-loaded valve. So as the pressure increases, the valve opens more, releases the steam, and as a result, the pressure drops. This is feedback in action. Now, here is a recap from the previous workshop. Who can actually identify the key points out of the come to the board and identify the key points on this characteristic control graph? So first, we can observe that there is a desired output, which, as the name suggests, is what we actually want to obtain. Then there is the actual output, and as the name suggests again, is what we got. Then there's a steady state in which the system will stabilize, the point in which the system will stabilize, and then there's the steady state error, which is the gap that will be created between the value that the output when the system was stabilized and the desired output. We can observe as well rise time. And the rise time is the time it takes the system to get close to the desired output. There's also the peak time. And the peak time is the time it takes the system to get to the highest point in the graph. So in this case, is after the overshoot. But what is the overshoot? The overshoot is like how much the system will surpass the desired output. So it's the gap that is created. Then, and that's it for now. Now, what about this image? Like we can observe three controlled responses, three different controlled responses. Which one is damp? Which one is over damp? Which one is critical damp? And which one is under damp? Can you actually differentiate which one is which? First, what is damping? What exactly is damping? So damping is a dissipation of energy in an oscillating system. So a good example to visualize this is when you pull a string. So if you pull a spring and then release it, if there is no damping, the spring will continue to oscillate forever. But with damping, the spring will eventually come to a stop. That is damping. So now that we know this, we can actually look at the three types of responses. So there is the underdamped response. And this one is characterized by having a zeta, a So now we can actually identify which one is which. Underdamp is a response in which the system will have a really low amount of damping, which allows it to actually oscillate with a decreasing amplitude over time. However, it will react quickly, it will respond really quickly, but it will create an overshoot. Then there is the overdamp, and it's the exact opposite as the underdamp. The overdamp is highly damped. It has a lot of damping. This will allow the system to actually respond slower, a lot slower, but it will not generate any type of overshoot nor oscillation. Finally, there's the critical damp. And this one is the ideal one. It's what all engineers expect from a system or are looking for when doing this type of graphs. So in a critical damp, there is no overshoot and there will be no oscillation, but the system will try to respond as quickly as possible. Then let's see the equations. So we have MP. MP is a maximum overshoot. And as we can see, this equation only is based on the zeta. So it is controlled by the zeta. But what is zeta? Zeta is a silly looking Greek letter. And this Greek letter is actually the damping ratio. So the damping ratio is like the division of the comparison of the mm, Now, what about this image? We can observe three control responses, three different control responses. Which one is over damp, which one is critical damp, and which one is under damp? First, we need to define what is damping. So damping is the dissipation of energy in an oscillating system. So a good example is a spring. So if you take a spring, you pull it and then release it. Without damping, the spring will continue to oscillate forever. But with damping, it will eventually come to a stop. That is damping. Now that we know that, we can actually start looking into more important concepts that will be repeated throughout this workshop. The overshoot occurs when the system exceeds the set point before settling. It is clearly visible in the underdamp, that is the yellow one. It's caused by aggressive control action or low damping. As the name suggests, underdamping has low damping, and this response is characterized by being really quick, but having an overshoot and oscillating before actually settling. So what are oscillations? Oscillations happen when the controller makes the output like dance back and forth across the reference value without ever settling on it. Now that we know what underdamp is, we can actually get what overdamp is. So overdamp is the exact opposite of underdamp. Overdamp means it's a system with a lot of damping, with highly damped. So in this type of system, the response will be slower, but the system will be more stable. The response will be more stable. There will be no overshoot and no oscillations. Finally, we have the critically damped. And this is the response of the system that is the response that we engineers want to get. It's the ideal one. So you will have that the system responds as fast as possible as to not at the limits as fast as possible as it can react without creating an overshoot nor oscillations. Now let's have a look to the equations that we have in the right part of the graph. So we have MP. What exactly is MP? MP is the maximum overshoot. And as we can observe, it is inversely proportional to zeta. Zeta is that silly looking Greek letter. But what exactly is zeta? Zeta is the damping ratio. It is how oscillations in a system decay after disturbance. Then we have another equation that it's actually how to calculate zeta. And zeta as well is inversely proportional to the maximum overshoot. So if you have the maximum overshoot, you can actually get the zeta. And then you can actually categorize which response your system will have: underdamp, overdamp, or critically damp. Finally, we have TS, which is the settling time. And the settling time is how long the system takes to enter and remain within a small band around the set point. So more or less in this part. Then we have that it's 4 over zeta, which we already know what it is, but there's another Greek letter. What is that Greek letter? That Greek letter is lowercase omega. And this one is natural frequency, and it represents how fast the system oscillates when we change its resting state. So we can visualize it like a swing. No matter how hard you push, the system always oscillates at the same rhythm. That is the natural frequency. Here's another key concept that you can actually use to identify which response your system will have. So you have that if zeta is smaller than 1, you will have an underdamped system. And it is characterized by a lot of oscillation, an overshoot, but a quick response. Then we have is zeta is equal to 1, you will have the critical damp. So you will have the optimal one, the ideal type of system. Finally, if you have that zeta is bigger than 1, you have an overdamp system, which is slow. It has a slow response, but is way more stable than the underdamp. But why are they important? Why do I need to know which type of response, which type of system I have? Well, in manufacturing applications such as FrED, excessive overshoot may lead to diameter fluctuations, while excessive damping may slow the corrections of disturbances. Therefore, this type of second order analysis is very important to balance performance and robustness. So now that we know this, we'll pass to implementing the first code we have in MATLAB. So please start by opening MATLAB.
Now let's briefly talk about different control techniques. Um, some of the most common control closed loop techniques are the on-off control, which just is the simplest. It fully switches the actuator on and off depending on whether the error is positive or negative, like the thermostat in your home. Fuzzy logic control uses linguistic rules instead of precise equations to control systems with uncertainty or nonlinear behavior. The adaptive control automatically adjusts its parameters in real time to maintain a performance when the dynamics of its system just changes a lot. And finally, the model predictive control predicts the future system behavior using a model and optimizes control actions over time. So yeah, and the star of today's show, the PID controller. It's a linear feedback law composed of three actions. Proportional action, which reacts directly to the current value. If you have a large error, you will have a large response to it. The integral action, which is the accumulation of error over time. Remember that by definition, the integral is the area under the curve, which means it helps eliminate when a steady state error, which is an error that just, as seen before, stays over the set point by a little bit of difference and it just stays there. And over time, that little error will accumulate into a much more bigger error and will trigger the integral action response, which will help eliminate that steady state error. And finally, the derivative action, which depends on how fast the error is changing. Yeah, and the objective of these three actions is to improve stability, reduce steady state error, and, like every controller, reduce or reject disturbances. Here we see the complete mathematical representation of the PID controller. It comes in three variants depending on which combination of actions is used. It could be P, PI, PD in some cases, or fully PID, which is the combination of the three, the proportional, integral, and derivative part. So just a reminder of the table that we examined before with Adrian, and a reminder of what I said before, the proportional acts on the current error, the integral on the steady state error, and the derivative upon the error's trend. When we represent the PID in the Laplace domain, we get a transfer function, which we will get to that in a little bit of in a few slides. And this representation allows us to apply powerful mathematical tools for designing and analyzing the closed-loop system we will be implementing on our motor.
Hello, my name is Diego. Let's discuss about power electronics. So, before applying our controller to the motor, we need to understand how the controller actually influences the physical system. In control theory, we compute a control with a signal called U on T. So, however, this signal is only a mathematical comment. To transform this command into real electrical energy delivered to the motor, we rely on power electronics. Power electronics is a field of electrical engineering concerned with the conversion, control, and efficient regulation of electrical power using semiconductor switching devices. In many systems, the available electrical power cannot be applied directly to the load. Instead, it must be converted, conditioned, and regulated. This is done through different types of power electronic converters. For example, we have rectifiers that convert AC power into DC, inverters that convert DC power into AC, and the image shown here is an example of a DC-DC switching converter, commonly known as a buck converter. This type of circuit is widely used in power electronics to efficiently regulate voltage levels and also regulate voltage levels between different DC sources. These systems operate by rapidly switching semiconductor devices, which allows precise control of voltage, current, and power flow, while still maintaining high efficiency. In the case of our FrED, power electronics is responsible for supplying the spooler motor with appropriate electrical power. The controller computes the control signal, and the power electronic stage translates that signal into the electrical power delivered to the motor. So yeah, control algorithms decide what the system should do, but power electronics makes it physically possible. Now that we have introduced the role of power electronics, we can discuss one of its most important implementation techniques, pulse width modulation or PWM. PWM is a method used to regulate the average voltage, and therefore the average power, delivered to a load by rapidly switching the input signal between two discrete states, on and off. The key parameter in PWM is the duty cycle, which is a fraction of each switching period during which the signal remains on the on state. Because the switching occurs at a sufficiently high frequency, the load responds primarily to the average value of the signal rather than to each individual switching event. This is why PWM provides an efficient way to emulate a variable input voltage without requiring a continuously variable analog power stage. We can see directly that in the figure. At a 25% duty cycle, the signal is on for only a quarter of the switching period, so the average voltage is approximately 1.25 volts. At a 50% duty cycle, the signal remains on for a half of the period, which increases the average voltage to approximately 2.5 volts. And as the duty cycle increases, the effective voltage delivered to the load will also increase. In the context of motor control, this is especially useful because the controller does not directly generate the motor voltage itself. Instead, it computes a control action and PWM translates that action into effective electrical input applied to the motor. So, in practice, PWM allows the controller to regulate the motor input through the duty cycle, while preserving high efficiency in the power stage.
PID controller pros and cons. Like any tool, like anything in the world, PID has its strengths and its weaknesses. Some of the advantages is that it's simple and intuitive, easy to understand, implement, and tune compared to advanced methods. It is widely proven in industry. It works reliably for a wide range of processes from, as we've seen, manufacturing fiber, optical fiber, to even drones, everything that could require control, it might work with PID. It's the most used controller in the industry, and yeah, it's really easy to tune, as I've said before, and some of the disadvantages is that it has no explicit prediction. It only reacts to errors because it's a reactive control. There needs to happen for the controller to react. Um, some of the definitions say that the derivative part could be seen as the predictor of the future, but that is actually wrong. You won't find that definition to the best of my knowledge, in any serious control book. So we won't even say that it predicts the future. And some poorly chosen gains can cause overshoot, oscillations, and instability. But what do we mean by tuning? Well, tuning means we are going to be able to find the adequate values for the coefficients that are called gains. These coefficients, there is no universal PID, so we need to find each PID coefficients, PID gains, for each system that we try to implement a PID on. And there are a wide variety of methods. We are going to present you with an analytical one. And yeah, just keep in mind that the goal of the system is to respond quickly, accurately, and stably to any given reference, and proper tuning balances performance metrics like the ones we've said before: overshoot, settling time, steady state error, and well, according to the application requirements. Here are some examples of tuning a PID with no particular method, just trial and error. As you can see, these graphs don't look great. The output actually doesn't track the reference very well, and this is what happens when you don't have a clear methodology for choosing your gains, which we will solve today. We're going to show you, as I've said before, an analytical way to find the adequate gains so your controller works efficiently. But first, we need to model what we want to control. We'll just wait for that to happen, and first we will get to try setting the gains in the FrED. So some of you give me a value between 2. Here, like in the audience, I ask for a PID gain estimation, just to show how the FrED will respond to these random values that will be given by the public. And we'll get to the modeling part, talked by my colleague.
Now, what is a model? A model is an abstraction constructed to answer specific engineering questions. So in manufacturing, there are common modeling objectives such as the prediction. In this, we engineers try to forecast process behaviors under changes in inputs, disturbances, or set points. Then there's the analysis. In the analysis, we try to study stability. We try to stability, sensitivity, and performance limitations given by physics. Then we have the control design. So in this, we designed feedback control laws to regulate variables and product quality. Finally, we have the optimization. In here, we trade off quality and energy consumptions under certain constraints. But why is it important? Why are we going to model? So we seek a model that is adequate for a defined purpose. In control, model adequacy typically means capturing dominant dynamics in the frequency band that are relevant to regulations and tracking, with an explicit representation of uncertainty when needed. So these dominant dynamics could be inputs, outputs, states, and disturbances. Now, transfer functions. What are transfer functions? A transfer function is a representation of a system through a linear, time-invariant differentiation equation. Mathematically, we can observe it as the Laplace transform of the output over the Laplace transform of the input. And the Laplace transform is a Laplace transform is an integration transform that changes a time domain function into a complex frequency domain function. So we need that all initial conditions are set to 0. Why? It means the motor, that way we make sure that the motor starts from rest with no stored current and no initial angular velocity. You can actually visualize a transfer function as how a system transforms an input into an output without telling us exactly what happens inside. So you can actually see it as a black box. So these transfer functions are only implemented when modeling SISO, which means a single input, a single output system.
Now let's talk about the transfer function of our motor. How exciting. Well, in this system the manipulated input is the voltage applied to the motor, while the measured output is the angular velocity of the spooler. The transfer function we seek to identify captures the dynamic relationship between these two variables. This is particularly relevant in FrED because the spooler speed has a direct effect on fiber tension, which in turn plays a major role in determining the final fiber diameter. Before deriving the transfer function, we first need to define the main variables and parameters involved in our DC motor. First, the input voltage, or VT, applied to the motor. In our case, this voltage comes from the motor driver as a PWM command, which effectively controls the electrical power delivered to the motor. Next, omega t represents the angular velocity of the spooler, which is the rotational speed of the motor shaft. This is typically measured in radians per second or RPM, and it is the main output variable of the system because it directly affects the fiber winding process. Then we have T of t, which is the torque generated by the motor. Torque is the rotational force responsible for accelerating the rotor and maintaining its motion. The variable IT represents the armature current, which is the electrical current flowing through the motor windings and is directly related to the torque produced by the motor, as we will see in some moments. Next, we have the VEMF, or the back electromotive force. This is a voltage generated by the motor when it rotates. According to the electromagnetic induction, the rotation of a motor in a magnetic field induces a voltage that opposes the applied voltage. This effect naturally limits the motor speed as it spins faster. The parameter J is the moment of inertia of the rotor. This represents how resistant the rotating system is to changes in speed, and it depends on how the mass of the shaft, armature, and other rotating components is distributed relative to the axis of rotation. Then we have the parameter L, which is the armature inductance, which represents the ability of the motor windings to store energy in a magnetic field and resist rapid changes in current. The parameter B is the viscous friction coefficient, which models mechanical losses that are proportional to the motor speed. Finally, we have Ke and Kt, which are our motor constants. Ke is the back EMF constant, which relates the motor speed to the induced voltage. Kt is the torque constant, which relates the armature current to the torque produced by the motor. Now that we've defined the system variables, now let's take a look to the equations that describe the system. The first equation is the mechanical equation of the motor. The This equation describes the rotational dynamics of the rotor. On the left side, we have that J and omega, well, dot omega, which in Newton's notation means that it's derivated with respect of time, uh, represents actually the rotational inertia multiplied by the angular acceleration, which corresponds to Newton's second law for rotational motion. On the right side, we have two terms, kt times I, or depending on t, that represents the electromagnetic torque generated by the motor, which depends on the current, and b omega t, that represents the viscous friction torque, which opposes the motion. So essentially, this equation states that the motor acceleration depends on the difference between the electromagnetic torque and the friction torque. The second equation is the electrical equation of the motor. This equation describes the voltage balance in the motor circuit. The applied voltage must overcome three different effects. First, R I of t, which is the voltage drop across the armature resistance. Second, all IT, which represents the voltage associated with the inductance of the windings, capturing how the current changes over time. And third, we have the back electromotive force, which opposes the applied voltage and increases with motor speed. In the diagram, it's shown that the representation of the electromagnetic structure of the motor. So we have the electrical side, where we can see the resistance and the inductance that are from the armature windings. The motor converts electrical energy into mechanical energy through the torque constant. Then, on the mechanical side of the rotor, we have driving the inertial load, represented by J, and experiencing the viscous friction, represented by B. The output of the system is the angular velocity, which is exactly the variable we want to control in our process. A DC machine converts electrical energy into mechanical energy through electromagnetic interactions. When a voltage is applied to the armature current, it flows through the windings according to Ohm's law. This current generates a magnetic field, and the interaction between the armature current and the magnetic field of the permanent magnets produce a force described by the Lorentz force law. This force results in a torque that causes the rotor to rotate. As the rotor spins, the changing magnetic flux through the armature conductors induces a voltage according to Faraday's law of electromagnetic induction. This induced voltage opposes the applied voltage and is what we refer as back electromotive force. An important point to take into account is that a DC machine is electromechanically reversible. But what does this mean? This means that it can operate not only as a motor, but it can also convert electrical energy, it can also convert mechanical energy into electrical energy, giving it a function also of a generation. So this is precisely why the back EMF is so important in the motor model, because it reflects the generator-like behavior that naturally spins when the rotor is spinning. Now that we understand the physical behavior of the DC motor, we can begin describing it mathematically. We start from the electrical equation of the armature circuit that we have on the top. This equation comes directly from Kirchhoff's voltage law. It states that the applied voltage must equal the sum of the voltage drops in a circuit. The first term, R, represents the voltage drop across the armature resistance. The second term represents the voltage associated with inductance of the windings, which accounts for the fact that the current cannot change instantaneously. The last term is the back electromotive force, which is generated by the rotation of the motor that opposes the applied voltage. To analyze the system more easily, we will transform it into the Laplace domain. The Laplace transform converts differential equations into algebraic equations, which makes it much easier for us to manipulate them. And to get our transfer functions. We can see that we applied the Laplace transform into our variables, and we can see the equation that now describes the dynamics of the motor, of the electrical dynamics of the motor, but now in the Laplace domain. And also we combine the electrical equation. Well, now we will combine the electrical equation with the mechanical equation of the motor in the next steps. Now, here is the mechanical dynamics of the motor. This, as we mentioned earlier, comes with the rotational equivalent of Newton's second law. So, we already explained this equation, and we can see that it is also in the Laplace domain. So, what we understand of this is that when we go to the Laplace domain, our variables become like in a complex frequency domain, and also just um, in uppercase letters. Together with the electrical equation that we derived earlier and this equation, we will try to input the voltage motor to its angular velocity, which is exactly the relation that we are looking for. So what we did is that we write the equation of the motor, and we took the Laplace transform of both electrical and mechanical equations. But then what do we need to do? Okay, so we had a term that was the current. And because the current is the internal variable that connects the electrical and mechanical parts of the motor, we isolate it. And then from the mechanical model. And then we substitute it back to the electrical equation. This allows us to eliminate the current and obtain a single equation that relates the input voltage with our output, our desired output, which is angular velocity. Finally, we rearrange that expression to obtain the transfer function, as we can see on the image. So there, where this says GS, it actually means capital omega, also in the S domain, over the capital D, that is voltage, in the S domain, which represents the dynamic model of the DC motor. So now we have to normalize the transfer function. But what does this mean? If you remember, in the last part of the equation, we had some coefficients uh, besides our S variables. But what does it mean to normalize? We have to actually divide for us to have the S squared coefficient with a 1. So here we can identify our parameters, which are B, A0, and A1. And let's go to the other slide. Now here we will tell the students that it's their turn, and they will have to use the parameters given on the slide to find the system's transfer function in a MATLAB code that it's already made. So, and also to identify the group values. Now that we have obtained the transfer function of the motor, we can introduce the controller that will regulate the system, in our case, PID controller, whose transfer function in the Laplace domain is the following, as you can see in the presentation. Each term corresponds to a different control action, which has already been explained. And we can see that in the block diagram, we can see a closed loop control structure. But also we have an open loop transfer, that is the controller times the plant. So we often start looking at the open loop transfer function. So the open loop transfer function is simply the product of the controller transfer function and the plant transfer function. So mathematically, we write as if they were multiplying. So GS in this case is our motor dynamics, and CS is the PID controller. This open loop representation is important because it allows us to analyze stability, system pulse, and controller design before closing the feedback loop. Now that we have both the plant transfer function and the PID controller, we can combine them. First, we have already computed the open loop transfer function, which is simply the product of the plant and the controller. And after multiplying both expressions, we get the combined dynamics of the controller and the motor before closing the feedback loop. And how do we close that feedback loop? So we use the standard formula for the closed loop transfer function of a feedback system, which is the one stated in the presentation. This equation describes how the system output responds to the reference input when feedback is applied. The denominator term 1 plus Js times Cs, captures the effect of the feedback loop on the system dynamics. After substituting the open loop expression and simplifying, we obtain the final closed loop transfer function, which is the one at the bottom. This form is very important because it expresses the system as a polynomial in S. From this polynomial, we can analyze the system poles, which determine the stability and dynamic behavior of the system. More importantly, we can see directly how the controller gains, Kp, Ki, and Kd, modify the coefficient and characteristic equation. This is what also allows us to tune the PID controller and shape the dynamic response of the motor system. Now that we have the closed loop transfer function, we can use it to design the PID gains. The denominator of the closed loop transfer function determines the system dynamics because its roots correspond to the closed loop poles of the system. From our previous derivation, the denominator polynomial is the one stated at the top. The polynomial, we can see that it depends directly on the PID gains. But instead of choosing these gains arbitrarily, we specify the desired dynamic behavior of the system. To do this, we define a desired characteristical polynomial based on the parameters that describe the system response, such as natural frequency and additional pole. This desired polynomial is the one that is below the one that we discussed earlier. The idea is simple. If two polynomials are equal, then their coefficients must also be equal. So we match the coefficients in order to make these solutions, which are our final PID gains. And well, these expressions are very useful because they allow us to compute the controller gains analytically based on the desired system dynamics defined by the parameters that we've discussed earlier. So instead of tuning the controller purely on trial and error, we can select the desired response characteristics and directly calculate the PID parameters that achieve the behavior. There's a problem. To compute these gains, we need to know the physical parameters of the motor: inertia, viscous friction, the constants, inductance, resistance, and in many cases, we simply cannot open the motor to measure them directly. But before moving into system identification, it is important to discuss briefly instability and instability in control systems. A system is considered to be stable if its output remains bounded for bounded inputs. In other words, if we apply a finite input to the system, the output should not grow without limit. In practical terms, stability determines whether the system behaves in a predictable and controlled manner. In the context of FrED, stability is especially important because the variable we're controlling is the spooler speed, which directly affects the fiber diameter. If the system becomes unstable, the spool speed may oscillate or grow uncontrollably. This would lead fluctuations in fiber tension and ultimately produce a irregular fiber diameter or break into it. On the other hand, A stable system responds smoothly to disturbances and corrections, allowing the spooler to maintain a consistent speed and ensuring uniform fiber winding. Mathematical stability is closely related to the relocation of the system poles in the complex plane, which we will discuss in the following slide. So, we can see in the figures that it illustrates this idea of an unstable response that is growing over time, while another stable response is gradually converging to equilibrium. So we will now analyze the location of the system poles in a complex plane. The poles of a system are the roots of the denominator of the transfer function, and they determine how the system responds over time. If the poles have a negative real part, they lie in the left half of the complex plane, and the system response decays over time. This corresponds to stable behavior. If the poles are located close to the imaginary axis, the system tends to exhibit oscillatory behavior, meaning the response oscillates before settling. However, if any pole moves into the right half of the complex plane, the system becomes unstable because the response grows instead of decaying. In the figure shown here, we can visualize these regions for continuous time systems. Stability requires that all poles lie in the left half plane. For discrete time systems, stability requires that all poles lie inside the unit circle in the complex plane. This is where control design becomes important, because one of the main roles of the PID controller is to modify the system dynamics by shifting the location of these poles, by properly choosing the gains of Kp, Ki, and Kd. This ensures that the system responds smoothly and avoids oscillations or instability. Since we cannot directly measure the internal parts of the motor, we use a different approach known as system identification, which consists in estimating the mathematical model of a system using experimental input and output data. One of the most commonly used techniques for this purpose is the least squares method, which is a mathematical method used to estimate unknown parameters by minimizing the squared error between two quantities. The first quantity is the measured output of the real system, and the second is the output predicted by the mathematical model. The idea is to adjust the model parameters so that the predicted response of the model is as close as possible to the measured response of the real system. By minimizing the squared error between these two signals, we obtain the best parameter that estimates and explains the observed data. In the context of FrED, this approach allows us to estimate the motor parameters and identify the system dynamics without physically accessing the internal components of the motor. So instead, we excite the system with known inputs, measure the resulting outputs, and then use least squares to determine the parameters that best fit the observed behavior. To estimate the unknown model parameters, we formulate the problem in the standard least squares matrix forms, which is the big equation in the presentation. This compact expression represents the relationship between the measured data and the unknown parameters we want to estimate. The vector y contains the measured output data of the system. The matrix X is called the regression matrix. It contains the known terms constructed from the input and output data of the system. And the vector beta contains the unknown parameters that we want to estimate numerically. So the goal of the least squares is to find the parameter vector that makes the model prediction as close as possible to the measured output. In other words, we choose the parameters that minimize the squared error between the measured data and the model prediction. The least squares formulation can also be represented as an optimization problem. Recall that our model was done. And however, in practice the model is not perfectly matched to the data, because the measurements contain noise and the model is only an approximation of the real system. So instead of forcing an equality, we define it as an error term. This error represents the difference between the model prediction and the measured system output. The goal of least squares is to find the parameters vector that minimizes this error. To do this, we minimize the squared error, which is written by the parentheses and the squared. Squaring the error ensures that both positive and negative deviations contribute to the cost, and it penalizes larger errors more strongly. For mathematical convenience, we often define the cost function as the one at the bottom. The half factor does not change the solution, but it simplifies the derivatives when solving the optimization problem. So now we obtain this optimization using matrix algebra. So recall that our objective was to minimize the squared error between the model prediction and the measured data. So we have our cost function. Using metric notation, this expression can be written more precisely as the product between that function and the transposed. Well, that function transpose and that same function. This represents the squared Euclidean norm of the error vector, and it defines the cost function that we want to minimize. So we denote this function as j of beta. So the problem becomes find the parameter vector beta that minimizes the function j of beta. To find the minimum of this function, we compute the gradient of the cost function with respect of the parameter vector beta. The optimal solution occurs when the gradient is equal to 0. This condition means that we are at a stationary point of the cost function, which corresponds to the minimum error between the model and the measured data. Solving this equation leads to normal equations, which provide the analytical solution for the parameter estimates. So now, having our cost function, we take its gradient with respect to the parameter vector beta and set it equal to 0 in order to find the minimum. This equation states at the optimum of the gradient of the error where its cost vanishes. Rearranging the terms, we obtain the operations in the middle. This equation is known as the normal equation of the least squares problem. If the matrix X transpose X is invertible, then we can solve explicitly for the unknown parameter vector. This is the closed form least square solution. Yes, that equation at the bottom. So this expression gives the parameter values that minimize the squared error between the model prediction and the measured data. For our system, these estimated parameters will later be used to recover the coefficients of the transfer function and describe the motor dynamics. Now let's make some hand-on exercises, when we will give you a least squares MATLAB code for you to calculate the following datasets. And that would be the finish of the workshop part 1, and the part 2 will be given by my colleague Patricio Gomez, that will have us exciting with inputs at the FrED for us to get the datasets and doing what we've been doing. Well, first cleaning, because we don't want missing values, outliers, noise, because we want to have a good system identification. And now we will use code to get our values of B, A0, and A1. This will be given in a MATLAB code. And then we will be starting to make the code. And after we run it and get our transfer function, now we will go to Simulink and start making our own diagram, our own block diagram program, which, as I said, will be given by Pato, to finally compare the graphs in MATLAB and Simulink with the real experimentation in FrED. Thank you for your attention.